Thank you very much for the introduction. It's actually a different topic, which was changed recently. So I think this is going to be interesting for you. It's the same one we explained in the brochure. So I'm going to be talking about similarity search. So you mostly all are aware of this search box that appear in mostly every website that we use nowadays. In today's world that instant retrieval of information has become the new paradigm, we want every second to count, and we want to access the information as soon as possible. So we are not going through different sections and subsections anymore. We want straight to look for it and then get the results back as soon as possible. Now, in this context, how can we improve this interaction and get the search results as possible and as accurate as possible? So today we're going to be talking about similarity search that hopefully is going to bring your search engine to the next level. Now, a picture is worth 1,000 words. So with that premise in mind, we're going to look into similarity search and explain how can we use words to describe what we're looking for instead of just typing ourselves what we're looking for. Sometimes it's much easier to upload an image of a, for example, address and find similar ones rather than us trying to describe how does that picture look like. So what's the agenda for today? First, we're going to start explaining how text search works. We're going to go through the basics, the analysis part, and the querying part. This is going to serve as a basis to then later go into image search. We're going to do the same process of analysis and querying, and we're going to see the differences between text and image search. And finally, we're going to go into an end-to-end architecture built on AWS on how to implement this similarity search. So let's start with the analysis part. When we talk about text search, we always start with a document. In a document, we have some kind of unstructured text that we want to have search capabilities on. So the first step is to go through a series of steps in order to make it structured and be able to save it in a data store that afterwards is going to allow us to retrieve that information that we are looking for in our searches. So what this analysis looks like. We have three main steps. So the first one we have is character filters. For character filters, one typical example would be to remove the HTML tags. So let's go through all these examples by explaining a very simple example, H1 DSC Europe 22 closing HTML tags. So first, we remove all the HTML tags that don't contain any meaningful information that we are of interest. Then it comes the tokenizer part. That is probably the most important one when we are working with text. We want to reduce the text into minimal pieces of information that we're going to use later for doing our search. So those are the tokens. So a simple token could be just to identify each of the tokens with a blank space. So in this example would be just 3 tokens, DCS, Europe, and 22. And finally, we can apply some token filters in order to homogenize the data. So a simple token filter could be to lowercase the data and keep it lowercase. So this is Europe 22. Once this data is structured or organized into tokens, we can later store it in the data store that is going to allow us later to query that data back from us. So how do we query this data? There's different data stores out there, different technologies that we can use. Most of them, what they use is a domain-specific language that allow us to access the different APIs in order to get the information we're looking for. So in this specific query, that is a match query, we are looking for the documents that contain the word Europe. So what happens first? The text we're looking for goes through all this analysis part that we just explained. So it goes through the filters, tokenization, and token filters, and we get the token that we want to look for. In this case, Europe. And then we take all the different documents that we have previously stored in our data store, and we compare it, and using a ranking mechanism, we retrieve back the result that better matches our search. So up to here, text search. Now, let's do the same process with image search and start looking at the differences between each of them. So when we do image search, we do the same process of analysis. We want to break the image down into smaller pieces of information to work better when we store it in the data store. What happens with an image? An image is a much more complex structure. You can think about an image of 1024 by 1024 pixels. That's in total more than 1 million pixels that we have in the image. Each of the pixels have red, green, and blue values, so that's more than 3 million data points to describe the image. How can we break down 3 million data points in order to reduce the dimension enough so we can store it in our data store? A first valid approach would be to start describing the image, right? So what we could do is take an image and start saying, okay, what do I see in the image? This is a dress, it's white, has a black bunny, short sleeves, round neck, you name it, right? You just try to describe it and you get these characteristics that could represent what the image looks like. There's two main problems with this approach. The first one is that it's time consuming. You have to go through every image trying to describe it as good as you can, right? And the second one is that it's very subjective. In the end, my description is not going to match yours, it's not going to match yours, or it's not going to match yours. So in the end, there's subjectiveness there in the process. So what can we do? What can be a better approach to follow to describe this image? Here comes the machine learning into the rescue, and we're going to be using convolutional neural networks. Can you raise the hand if you have ever used or heard about convolutional neural networks? Okay, nice. Most of you. The ones that you have not, please stay with me because it's not that important. So what I want you to keep in mind is that the objective of using a convolutional neural network is to reduce the dimensionality of the image. We said that the image has a lot of data points. We want to reduce this dimensionality and try to keep all the information in a more compressed way. So what it happens is that the image goes through a series of layers, and in each of the layers, we reduce the dimensionality. And the objective is to reduce the dimensionality enough so the same information that was contained in the image can be described as a vector, as a feature vector. In this case, in the last layer, we have 1,000 data points that describe this previous image on a way that is much better than I could do it just by describing it by myself. Here you're going to see it a little bit better, what it happens. So take, for example, this car, and it starts going through the convolutional neural network. What it starts to happen is that on the first layers, what starts to happen is that the CNN starts recognizing small patterns, start recognizing colors, some lines. Then, as it goes through the convolutional neural networks, on the middle layers, start recognizing some bigger features. So it starts recognizing some patterns, start recognizing some shapes, circles, etc. And then, on the last layers of the convolutional neural network, what we actually have is great descriptions of the image. So, for example, we have here the wheel of the car, or we have a window, or we have the front side of the car. So these descriptions are much better than the ones I could use myself to describe an image, and much more numerous. Are going to be 1,000 values that are going to represent this image instead of my 10, 12 words that I was using to describe it previously. So up to here, the analysis part. Now, what happens when we want to search for images? As you remember, when we were searching for text, what we were doing is take the text we were looking for, reduce it into a token, and then finding this one-to-one relationship with other tokens. So we were having the token Europe, and we were looking for all the tokens that were Europe. So that's one-to-one search. What happens with an image? An image is not the same as any other. So all of them are unique. So what we do instead is to try to find the one that is most similar to the others that we have. And that's why it's called similarity search. So we talked about this 1,000 description of the object, the feature vector. Let's try to do it a simpler example, imagine that the image will have been reduced to just 2 data points, so x1 and x2. Let's say that we have this data point, and we want to find the ones that are most similar to the other images that are also represented by feature vectors. What we can do is to use the KNN algorithm. The KNN stands for key nearest neighbors. And what it does, it measures distances. So it measures the distances between that feature vectors and other vectors that we have stored in our data store. So, for example, one distance could be the Euclidean distance. So that's the formula right here. And we calculate this distance with our vector of interest with all the other vectors. And in the end, what we're going to get is the ones that are the closest. So in our example, for example, we have here k equal to 5. So that's going to get us the 5 points that are the closest and are the ones that we're going to retrieve back in our similarity search. KNN is usually used for classification. And that's why here in this example, we have these 5 data points. 3 belongs to category A, 2 belongs to category B. Here, what is usually done afterwards is say, okay, we have more of category A, so this data point belongs to category A. In our case, we are not doing this last step. We are skipping that step because for us, these 5 points that are the closest are the ones that are most similar to the image of our interest and are the ones that we are going to retrieve back. So let's do a recap. Here we have the whole search pipeline. So we start with address. Okay, let's start with an image of address. We want to reduce the dimension of it. We want to extract all the meaningful information into a feature vector. For that, we're going to use a convolutional neural network to get the features that describe this image on a more precise way. Once we have the feature vector, what we're going to do is to use the KNN algorithm in order to find the feature vectors that are on a closest distance, so they are more similar to the image that we are searching for. And finally, those feature vectors correspond to specific images that are the ones that we are going to retrieve, and in the end, these 3 images are going to be the ones that we give back to the user. Now, enough of theory, so let's see how would we building this solution by using AWS components. There's 2 main protagonists for building this solution. The first one is OpenSearch. OpenSearch is an open source community-driven project that what it provides you is first a search engine that you can use for implementing your search. Then you have OpenSearch dashboards. That is a user interface that allows you to interact more easily with the project, and then has a series of plugins in order to improve the functionality. In this case, we would use the plugin of KNN to do this KNN search in the last step. In order to run OpenSearch, what we can use is the Amazon OpenSearch service. That is a managed service that allows you to run OpenSearch in the AWS cloud. And basically what it allows is to provide better integration between the APIs that controls OpenSearch with the other APIs that controls all the other AWS services. It allows you to have it fully managed, so you don't have to manage the infrastructure that is underneath it. So all the patches, all the installations, everything is done for you. Then it comes along with a set of features for security, availability, and compliance. And finally, there's other cost-effective options. The one that is very interesting is the one in which you can decouple the part of compute and storage by using storage of Amazon S3 instead of storing the information at disk. That is more expensive. So when you deploy a domain, basically it looks like this. OpenSearch is a distributed system, so it's composed by a series of nodes. There's the data nodes that contain the data you're storing, the ultra-warm nodes that we mentioned that come along with the Amazon S3 storage. Then there's the leader nodes that what they do is to orchestrate all the different data nodes. And then, of course, it comes along with a series of integrations for security, in this case with IAM or SAML. And then we also have other integrations for to easily insert information into Amazon OpenSearch. The second one is Amazon SageMaker. Amazon SageMaker is an end-to-end service to develop machine learning models. So you can control all the pipeline from the data collection and data cleaning up to the productionization, putting it into production, the model, and be able to make it an endpoint to get more easy access. It has a whole set of features. In our case, and for this solution, the notebooks, Jupyter notebooks, come very handy in order to create all the different steps that we're going to be building. Then also the part of training the model. We can train it from scratch, or we can use some pre-trained model by using some higher level libraries, like for example, Keras, that they come with some pre-trained models, which comes super handy in this case. And then for the deployment in production, we also can use some of the SageMaker APIs in order to put it as an endpoint. So you can just send the input and then get the return back. So in this case would be the input, the image, and the output, the feature vector that we are interested in. Now, this is a high-level architecture, end-to-end. So this could be if you want to create a website that has the Similarity search implemented. You could have the user. The user is going to interact via the browser. So the front end can be composed by static content, so HTML, CSS, JavaScript, that is going to get loaded into your browser, and you're going to use it to interact with the application. There can be a series of ways in which you can upload an image to find the most similar ones. And then when you upload that image, that could trigger an API call that we can configure with Amazon API Gateway in order to connect to our backend. And our backend is going to do the heavy work for us in order to find the similar images and return it back to the user. So for the backend, we can do it on a way that is serverless. So that's by using AWS Lambda. AWS Lambda is great because you don't have to manage the underlying infrastructure, and you can just write the code. In our case, our Lambda would have to do three main things. The first one, the analysis part that we talked about, is calling the Amazon SageMaker endpoint to get from the image the feature vector back. That would be the first step. Then the second one would be to do the search in Amazon OpenSearch. So basically, the input for OpenSearch would be the feature vector, and the output would be the feature vectors that are most similar to that one that we are looking for. And finally, what we could do is to retrieve that information in high quality from an Amazon S3 bucket. So in this way, we can lower the costs of storage of the images, and then once we have it back, return it to the user with all the images that are the most similar. Now, let's focus on the part of the backend. That is the part that takes more time and is the one that is closest to our topic now. So we have to do three main things. So the first one is to build the model and to deploy it into an endpoint in SageMaker. So for all these interactions, of course, everyone has different ways of dealing with this. I usually use notebook instances. They can be very handy. They are interactive, and you can do it step by step. So with SageMaker, you could create a model. You can use a pre-trained one, as we said before. Keras, you download a pre-trained one. You remove the last layers. We keep the feature vector. And that model, then we containerize it, and we deploy it as an endpoint. And with this endpoint, we can get access to it, so later our Lambda function can access to it. Then we have the Amazon OpenSearch service. Here, what we have to do is first use our SageMaker endpoint with all the images that we want to work with, make them go through the endpoint, and extract all the feature vectors. Once we have all these feature vectors, we are going to be storing them in Amazon OpenSearch. So later, when we are searching for a new image, we're going to be using these feature vectors to find the one that is closest to the image that we're looking for in this case. And finally, we're going to be storing all our images in our Amazon S3 bucket. So later, our AWS Lambda function can access to it and retrieve it back to the end user. So that's all for this session. I know it's a lot to put together in such short amount of time. I hope you learned something today. I'm open for questions. Thank you. You can provide me some feedback here. I have a set of interesting links that you can get access through here. So, yeah, thank you very much.
Yes. Do we have some questions? Okay, here.
Thank you for your talk. I have a question about feature vector creation. More specifically, which machine learning tasks are you using to train the network? So is it just categorization and tagging, or is it also some kind of triplet matching learning? So maybe you could give us some insights in how do you actually get the feature vector for image similarity.
Mm-hmm. Yeah, so this part of the solution would be the one that you can, let's say, work more on, right? Because in the end, you can start working with a pre-trained model. The pre-trained model should be or must have been trained on a data set that is similar to the images that you're using. So in this case, for example, what I tested would be a ResNet CNN that was trained on ImageNet, and ImageNet was having images of clothes. So in this case, the information that was able to retrieve was pretty accurate in this case. But if the images you're working with and you want to extract similarity are not in the categories of that pre-trained model, then it's the point where you would have to go and build it yourself, which of course is going to take more time, but that's the way.
And then basically it's categorization task as well, just as for the ImageNet dataset. So it's the same type of training. That was my question about. So is it the similar task?
Yeah, it would be a classification, but then afterwards, in the end, you're not classifying. So you're just using the CNN to extract the features. At the end, what happens in a classification with a CNN is that those 1,000 goes down into the number of categories that you have, and that's why that's how it classifies. So instead of going all the pipeline down to the AB3 categories that you have, you just care about the feature extraction that the work that the CNN is doing previously to get to that conclusion. So you would train it as a classification, and then you wouldn't care that much about the classification itself, but more about the information that gets stored through the process of the training.
Yeah, thanks. I understand how this process works. Okay. I'm doing similar things. I was just asking whether you're doing some different tasks like metric learning, things like that, and not just the tag prediction, but basically you're just saying it's categorization and possibly some tagging, like attribute prediction, possibly also have some tasks like that to get the fine-tuned model. If you got my question.
I'm not sure. What we
can
do.
Maybe we could talk later. So just
let's talk later and expand this. But
okay,
sure.
Thanks.
Thank you.
Any other question? I don't see any. Okay, here.
Thanks. How much time do you need for similarity retrieval? I mean, KNN could be really slow if you try to search a huge data set and try to find the most similar things to the one that you search. I mean, it's a long damn time to find those.
Totally. Yeah, great question. In OpenSearch, what you have is different variations of KNN. That basically what it does, it takes a random amount of samples in order to work on that, in order to reduce the amount of time. So you can play with those parameters. So let's say that your model, your application is time sensitive and you need the retrieval in less than X milliseconds, then you can play with the amount of random samples that is going to be used. So it's not KNN on its purest, but it's like a approach.
Some kind of approximation, right?
Exactly.
So, okay, thanks.
Exactly. Thank you.
Any more? If not, Francisco, thank you very much for this presentation.
Thank you.